So this is lecture 21 on linear algebra. This lecture is on quadratic form, rank, and signature. So what is quadratic form? The quadratic form is like, say, a11 x1 square plus a 22 x2 square, or say a xn square, then a12 x1 x2, like that. So it is actually aij xi xj, sum over that I and j. Or you may write in this form bij, then xi xj I less than j, less than or equal to 1. Now the corresponding matrix is this. The corresponding matrix is A, which is aij. Now say for example, say two variables, say 3x squared, 2xy plus say 4y squared. Now what is the corresponding matrix? Corresponding matrix is, you can write 3 4 here, but you can write say 2 0 here, maybe say 2xy plus 0xy yx, or you can write 2 3 4 1 1, same thing. So two different matrices have same quadratic form. So if you take if you have a matrix say aij, then the corresponding quadratic form is this. This is the corresponding quadratic form of matrix aij. And so once this quadratic form is given to you, you can generate many matrices. So for a matrix, there's a unique quadratic form, but for a given quadratic form, you have a more than one. It is not unique. The matrix is not unique. So we actually deal with the quadratic form, not with the matrix. We should not go from the matrix to the quadratic form. We start from the quadratic form and we come back to the matrix. So which matrix we will take? The thing is, we will take a symmetric matrix. So quadratic form, for a given quadratic form, we will take a symmetric matrix. So that means for say bij, this is, you have to take a matrix aij. If the corresponding matrix is say aij, a matrix aij here, so you have to take then aii is equal to bii, but you have to take aij equal to aji is equal to actually bij by 2. Remember, here we take just bij I less. And if your form is like that, cij xi xj, that I and j from 1 to n, in that case the corresponding matrix is A, then aij equal to cij, as ai equal to ci, and aij is equal to aji is equal to actually cij plus cji by 2. So for a given matrix, say B is a given matrix, you can always generate a matrix A such that the quadratic, by the way, this quadratic form is for corresponding A is x transpose bx. This is a quadratic form where x is just x1 x2 column vector. Now A transpose bx, B is a given matrix, and that is actually, you can write as x transpose B plus B transpose by 2. So this is your x A, and this is a symmetric matrix. B plus B transpose by 2 is the symmetric matrix, and these two quadratic form is same. Why? Because x transpose B x is actually same as x transpose B transpose x. So that's why x transpose Bx plus x transpose B transpose x by 2 is, these two are equal to this, which is actually this. And why these two are equal? Because this is just a number. So since it is just a number, you can take the transpose, and transpose will be same as that now, which is X transpose B transpose X. So we can for a given matrix we can change to a corresponding symmetric matrix such that that symmetric matrix and that given matrix are the same quadratic form. And for a given quadratic form, you can always unique there is a unique symmetric matrix which correspond to the corresponding quadratic form. So we will always take that symmetric matrix. There is a two advantage, that is a unique, and that symmetric matrix has the all the eigenvalues are real and such a properties are there. So now we have to classify all this quadratic form with respect to that corresponding symmetric matrix. Now classification of the quadratic form is non-negative definite. What is non-negative definite? This non-negative definite is this. So we take A as a symmetric. From now onward, we'll take that matrix as a symmetric matrix. X transpose X A, if it is greater than or equal to 0 for all X in Rn, then this is called non-negative definite. Non-negative, so it's never negative. Similarly, non-positive definite. Non-positive definite is X transpose A X is less than or equal to 0. What is positive definite? So positive definite is this: X transpose A X is greater than 0, strictly greater than 0 for all X greater than all X in R. But you can't take X as 0 now, so X not equal to 0. You can write X not equal to 0 here, but is not important. You can write or may or may not. So if you write this or you don't write this, this is equivalent actually, because X is 0 means X transpose AX is 0. But for greater than, strictly greater than, you should write X not equal to 0. Like a strictly monotone or monotone increasing, strictly monotone increasing and monotone. For strictly monotone, you have to write X greater than. For monotone increasing, you can write X greater than 1, you can write X greater than or equal to. Similarly, non-negative definite. What is negative semi-definite? Negative semi-definite is actually non-positive, but not negative definite. So what is semi-definite? It is non-positive definite as well as not negative definite. So remember that negative definite is non-positive definite. Any positive definite matrix is non-negative definite, because this implies this. So any positive definite matrix is non-negative definite. But there are some non-negative definite which is not positive, and that is called positive semi-definite. There are some non-positive definite which is not negative definite, that is called negative semi-definite. So what is negative semi-definite? So negative semi-definite is this: X transpose AX. So it is negative, so it should be greater than or less than or equal to 0. That is, it is a non-positive definite for all X. And at least there is at least one X which is non-zero, so that X transpose S for at least one X it is negative. So it is negative semi-definite. Oh, sorry, is equal to 0. So at least one non-zero, this is 0. So this is negative semi-definite. Similarly, negative. And what is indefinite? Indefinite means for some X, at least there is at least one X which is positive, at least one X which is negative. So it is called indefinite. So if you have there is no product term, say if you have only this squared terms, then it is clear when it is positive definite and positive, non-negative or semi-definite, indefinite, it is clear. If all the AIs, sorry, you should write A1, A2. It's only there is no product term. In that case, if A1, A2, AN are all positive, that means it is positive definite. If some are 0, some AIs are 0 and some others are positive, then it is non-negative definite, clearly. It can't be negative. If some AIs are negative, some AIs are 0, then it is
it can't be positive. So non-positive definitely. If all these ai's are negative, that means it is not negative. And if some are positive and some are zero, that is actually positive semi-definite. And some are negative, some are zero, that is positive negative semi-definite. And if some are positive and some are negative, or some are positive, some zero, some negative, that is indefinite basically. And this actually for the diagonal matrix. So corresponding diagonal matrix. So some result, the result, one important result for this quadratic form is this: x transpose Ax is 0, then it is null matrix. So it is null matrix basically, not 0, it is null matrix. And this is 0, this is real number. So if this is true for all x, then A is null matrix. You can do take first. How do you prove it? So if you take x as say 1 0 0 0, then you will get A1 is 0, and similarly you find all ai are 0. Then how do you prove that some element in off diagonals are non-zero, is 0? Remember, A is symmetric matrix. Since A is symmetric, I'll prove it that we say something is non-negative here. Say some t which is non-zero. Then actually you will get right. If we take say 1 1 transpose say 1 1, that means, or you can take 1 1 0 also. No, what happened? You just do it for 2. Take so it is say a1 1 a1 2 is again a1 2 a2 2. We take 1 0 1 0, then it is then it is just a1 1. Sorry, it is right. It is a1 1. Yes, it is a1 1. Right. This is a1 1. Then a1 2. Right. It is a1 1. So it is 0. So a1 all ai's are 0. Then you take just a1 1 1 1. Then take a1 1. Take 1 1. Then what happened? Then it will be a1 1. It will be then all the sum a1 2 plus a2 1. Right. Already you have these two are 0. So this is 0. Similarly, if you have 3 3 3 by 3, you will take 1 1 0. First all the diagonals are 0, then take 1 1 0, then this fourth terms will be some 0, then from this a1 towards 0, take then 1 0 1, then you will have you will get a1 3 0, then you will take 0 1 1, then we will find a2 3 0. And for n a similar idea, you will just first single one, other rest are 0, you will get all diagonal elements 0, then 2 at a time at ith position and jth position 1 1. Then you will find aii plus aij plus a2aij plus ajj 0. So aij is 0. So symmetricity is important here. So A is symmetric. Okay. So now the idea is next idea is this. So if you have a say X transpose A is a quadratic form, and you just take a transformation like y equal to px, then this transformation gives actually y transpose. Sorry, if you have transpose A or okay is
So x equal to you put x equal to p py. You put x equal to py. So in that case, you have y transpose p transpose a p, and then it is y. Now, if P is non-singular, matrix, then whatever. Then actually you have this from that you can find y also, y equal to P inverse x. Now these two are different matrix, A and P transpose AP, but these two have the same classification. If the left hand side is positive definite, then the right hand side is also positive. And if right hand side is positive definite, then left hand side is also positive. So it is actually these two things, this and this are equal. So the positive definiteness, this thing are equivalent. So A and that P transpose A P, these two matrix, because for every x we have a y and for every y you have a x. That means for some y, if you get this right hand side, and corresponding x we get the same thing in the left hand side. So if this is positive for some y, then this is positive for that corresponding x. So if it's positive for all y, then it is positive for all x. So that means these two matrix, once by if you just by a transformation, these two have the same definiteness. If it's a negative, if both are same, one is positive definite, other is positive. One is positive semi-definite, other is positive semi-definite. And this this is called, this say it is B, then A and B is called equivalence, is called congruent matrix. This is called congruency, and this congruency is actually equivalence relation. So if so what is A and B is called congruent if there is some non-singular matrix P. Non-singular is important, otherwise this every x we have a y, and for every y there is a x. That is important. So for a non-singular matrix P, if B equal to A P transpose AP, then A and B is called congruent, and this congruent relation is actually, say this relation is equivalence relation. You can easily check that. Now idea is this: so if you have a matrix A, and we want to find that proper non-singular matrix such that this is a diagonal matrix. Once this is a diagonal matrix, if A is congruent to the diagonal matrix D, because for the diagonal matrix, this quadratic form is easy to verify this whether the quadratic form is positive definite or semi-definite or other things. So, and we know that diagonal matrix and that A matrix, that P transpose AP and that A matrix has the same definiteness property. That is easy to check. We already checked this. And that for the diagonal matrix corresponding that P transpose AP, that we know easily that whether it is which property, which class, definiteness class. And so once we get this P transpose AP is some positive definite, that means A is positive. So we have to actually diagonalize in this way, that we have to take P transpose AP in the congruency way, not in the P inverse AP. In the similarity, we take the P inverse AP. You take P transpose AP. It's congruency. Once this P is orthogonal, that is easy. On this P is orthogonal, that means the P transpose and the P inverse is same. So this is the idea. We have to diagonalize this matrix by a suitable non-singular matrix. So reduction of the quadratic form. So the one more the most important theorem is this: any quadratic form remember that A is symmetric. Any quadratic form can be reduced to a diagonal form by a suitable non-singular transformation of the variable. So always there is a P, non-singular P, such that P transpose A P is diagonal. So this is, you can always reduce this in diagonal matrix. What is the proof? The proof is just by the spectral decomposition. Since A is real symmetric matrix, by the way, that A is real symmetric. That in the quadratic form is a real quadratic form. Forget to tell this. So A is a real symmetric matrix. Since A is a real symmetric matrix, we know there is an orthogonal matrix P such that P inverse AP is diagonal. So for a real symmetric matrix, this is diagonalizable. And the P inverse, there is a orthogonal matrix P transpose. For a real symmetric matrix, with this P is actually orthogonal. We can make this P as orthogonal. We need that orthogonal basis for that. The P is actually all the vectors. So we can take P as a orthogonal using Grant-Mess orthogonalization process. So that P inverse P is a diagonal matrix. And now this is P is orthogonal, this P transpose is actually P inverse is P transpose. So we are true. So we take that X equal to that Py, that change. Now these are congruent matrix, and that any quadratic form, if you have any quadratic form, we just first take that A real symmetric corresponding real symmetric matrix, that A, and then find that P for which the orthogonal matrix P, for which this D is the diagonal matrix. So D is congruent to that matrix A, and then we just find whether that A is what, that positive definite or semi-definite. Can easily find using the D. And if you D have all the elements are that means all the diagonal. If all the diagonal are all positive, then it is positive definite. If some are 0, other are positive, then it is semi-definite. So question is, how many are diagonal elements are positive or how many are negative? And that have some one more thing that is called signature. Now, what is signature? The signature is this. So if say PA is the number of positive term in the diagonal for the diagonal reduction, and NA is the number of negative term in the diagonal reduction, number of negative diagonal term, and this PA plus P is actually the rank, the number of non-zero terms in the diagonalization, diagonal matrix, and PA minus NA is called the signature. This is the signature of A. This is a signature. And this Sylvester law of inertia is this: if let there is a quadratic form, say X transpose A, X is a quadratic form, and this transform to a diagonal form, say Y trans is transposed to the say Y transpose BY, B is a diagonal, and say if another diagonalization process, say Y Z transpose CY, Y and Z, sorry, this is Z. Y and Z are both non-singular. If you have two different diagonalization thing of the diagonal BRC and both diagonal, then the number of positive terms Y and Z may not be orthogonal. If you have two singular, just non-singular P and Z, the number of B and C may be different, but number of positive term in B is same as number of positive term in C, and number of positive term in B, number of negative term in B is same as number of negative term in C. So, and obviously the rank of B and rank of C is same, and also the signature is same. So once we have the rank of if rank of A, rank of, and the signature, from that you can find number of positive and negative term. And similarly, if you know the positive and negative term, you can find the rank of and signature. Now, if say we let this take as a P, and this is an N, and rank is say R, and signature is say S, then there is a quick result is this: say if A is positive definite if and only if that S equal to P equal to N. That is actually equivalent to S equal to N. P equal to N means that is N equal to 0 and R equal to. So S equal to N. Full rank. Non-singular actually. Positive definite is actually non-singular. Then A is non-negative definite. What is non-negative definite? That means some term must be 0. So it is that means, but cannot be negative term. So is N equal to 0, and that is if and only if equivalently it is actually R equal to S, rank equal to signature, N equal to 0. Similarly, non-negative definite if and only if N equal to N, and equivalently equal S equal to minus N. And it is negative non-positive definite, then it is just P equal to 0. So P equal to 0, non-positive. So number of positive term is 0. Maybe some 0, maybe some negative, some negative. Equivalently R equal to minus S. And it's indefinite if and only if that P is greater than equal to 1 as well as N is greater than equal to 1. And equivalently mod S is less than R. The signature is, the mod value of the signature is less than the rank. Then it is indefinite. It is quick, you can easily verify this. And the important result is the symmetric matrix is positive definite or respectively non-negative definite if and only if each eigenvalues of A is positive. If all the eigenvalues of A is positive, then it is positive definite, and if it is positive definite, all these eigenvalues are positive. Similarly, if it is non-negative definite, all the eigenvalues are non-negative, and if all the eigenvalues are non-negative, then it is non-negative definite. And further result on this non-negative definite and if positive definite, we will in the next lecture, the last lecture.